Welcome to the video about weak bases. A lot of what I'm going to say is pretty much the same thing as weak acids. So just like weak bases, just like weak acids, a weak base will only partially ionize. For a base, you usually have to add the water in there because the base accepts the hydrogen, so it's got to accept it from somebody. So it has to take it from water typically. So because this is not a just regular forward arrow, then the concentration of hydroxide is going to be somewhat less than the concentration of the weak base. And so therefore the question is, of course, then how much do we have? And again, just like for a weak acid, you can do a Rice table to figure that out. But there's a hitch that you have to keep in mind. And I said this was going to be important on the weak acid. When you find X, for the weak acid, we found X, and X was the hydrogen ion concentration. We took the pH, the negative log of that, we got our pH. When we find X in this case, X is the hydroxide ion concentration. So instead of writing a Ka, we're going to write a Kb, which just means the base equilibrium expression. And so that is going to be our ammonium times our hydroxide over our ammonia. Water doesn't belong because water is a liquid. Liquids don't belong in the Kb expressions. So then when we find X, X is here. And so we're going to solve for X, and X will be the concentration of the hydroxide ion. So if we take the negative log of the hydroxide ion, we're not getting pH, we're getting POH. And hopefully you remember that pH equals 14 minus POH. So a base is just like a few steps longer than an acid as far as finding the pH of it, and that's only because we have the hydroxide ion instead of the hydrogen. So that just keep that in mind as you're doing these kinds of problems. Okay, but everything else is pretty much the same as for a weak acid. So who are the weak bases? You have two categories of weak bases. One, they could be a neutral substance. If they're a neutral substance, they have to have an extra pair of electrons to accept that hydrogen ion. So, for example, ammonia is a very common weak base. Ammonia has nitrogen, and nitrogen has an extra pair of electrons here. You can also make what's called an amide, and we're going to talk about those more in a future unit. But an amide is basically take an ammonia, lop off a hydrogen, and attach something else, especially an organic molecule. And you have something called an amide. But it still has nitrogen in there, so it still has that lone pair of electrons. So all of these are weak bases, and then also anions of weak acids. We talked about in class, the conjugate of a weak acid is a weak base. So if we start with a weak acid, it'll wind up as a weak base. And again, I said, you're going to see it as a salt, because you can't just have ions floating around there, but this would have been the conjugate of hypochlorous acid. So hypochlorous acid loses that hydrogen and becomes hypochlorite ion. And hypochlorite ion, just stick any old cation on there, and you have the weak base. All right, now how do Ka compare to Kb? So here's an equilibrium expression for Kb. We wrote equilibrium expression for Ka before. The way that they compare is, if we go back to basically a Hess's law kind of thing, here is a base reaction, base. And here's an acid reaction, the reverse reaction. Essentially, here's our weak acid ionizing. If we add these together Hess's law style, then we get the auto-ionization of water. Like that. Okay, so any acid-base reaction combination, if they're conjugates, will give you the auto-ionization of water. Now, ionization of water, this is a liquid. So if we were to write the Kw, water gets its own special one because water is special, that would be the concentration of hydrogen ion times the concentration of hydroxide ion. Kw is a constant, and you should know the number for this constant. It equals 1 times 10 to the negative 14. So any Ka times any Kb is going to give you Kw, because if you take the Ka, here's a Kb for this guy, here's a Ka for that guy. If you add two reactions together, you multiply their equilibrium constants. So Ka times Kb equals Kw, which equals 1 times 10 to the negative 14. If we were doing this in the P form, So P just means take the negative log of it. So if we did that, you have pKa. And if you take the log of two numbers that are multiplied, it's the same thing as the log of one number plus the log of the other number. So that becomes, that multiplication is plus. So P times pKa plus pKb equals the negative log of 1 times 10 to the negative 14, which is 14. So that's how Ka relates to Kb, which is a useful trick sometimes when you hit equations. And you can even use that up here if you wanted to find, instead of going to Kb and finding the OH and going back and find the pH after the POH, you could do Ka times Kb if you happen to know the Ka. So I'm only going to give you the appendix D of the Ka, and the appendix D for the Kb is very small, meaning that if you happen to have an equation where you're dealing with the conjugate base of one of these guys, I don't have to give you the Kb for it. You just take the Ka, and it's 1 times 10 to the negative 14 divided by the Ka to find your Kb, and they'll expect you to be able to do that. So, in short, weak bases are very, very similar to weak acids. Just remember that the 9 times out of 10, the question's asking for pH, and so you just have to keep in mind that you have to transfer your hydroxide into pH. Thank you.